Someone asked me to describe what's wrong with our data and how we deal with it. Okay, it's a question of strength. So you have to understand, we are on the roadmap to our operations. So we need to demonstrate to our colleagues that we are well aware of what's happening in real life. It's not the typical best example that we can present at the conference. This is real life with all the difficulties that are out there. Okay. So first, I will quickly describe what we are detecting, how we detect these TIDs, what are the sources of the data that are going into the forecast algorithms. And then we'll look at the 4 different resources that we use to as a indication of that TID is in progress. TID catalogs, and I put the strictest quality control, meaning we had humans, that looked at the data and made sure it's clean. That was done in order to train our neural nets, so that we wouldn't have the garbage in, garbage out getting into the training process. And then the other 3 items are real-time data, which is noisy, as we all know. And I would say HFINT technique is an elaborate system of quality control in place. The HFTID technique did not pass our requirements. We are currently even not considering it for operations until we have a stronger solution. And I will explain, I will show you typical best examples and not so best examples. And the last item is about GNSS detection in the VTEC and various time series and kilograms. And I would say it's an advanced quality control system in place as well. So here's a TID. We typically show it as a transverse wave, meaning you see that there's a wave which is propagating in that direction with this angle. And it's a modulation, transverse, meaning that no plasma is transported, no plasma is moving, it's just up and down, just like a stadium wave or your water park with the waves. So, which means what? If you are looking at it from the bottom, right, we should see it like vertical sounding, we should see that basically HMF2, the height of reflections is varying up and down, which is correct. But we also see it in terms of density. Why? If it just moves up and down, we shouldn't see that. So it's a good question. So even the best of us think that there's a longitudinal wave also included. That's why all this stretching is happening in the horizontal direction as well. That's why we see it in the FOF2, for example, very common FOF2. So it's only that FOF2 is not that well described. That TID is not very strong. HMF2 is a noisy data set. We know that, right, Matthew? You've been arguing for the noisiest possible HMF2 out there is there. Okay, so what do we do? And it's very tempting to just declare that we are so good, right, with HF versus other techniques, just because our probing signal of the ionization can reach specific area in the ionosphere, right, and check how it behaves with time. That gives us very high sensitivity to even minor TIDs, like a 5% of the modulation in the density, which will not show up anywhere else. We see it very quickly, very clearly. And one of our key experts on the TID detection with the HF would say TID are always present, and we see them. Okay, there are no other transform. If you look at this lovely contour plot, there's definitely something going on. You see the up and down and the vertical structure. So one clear possibility is just to stay in one of those lines and see how it behaves in time. This is not a clean data set either. We have data issues. We had to rule out that possibility as well. So HMF2 is out, FOF2 is weak. the contour plots of the isodensity is kind of also noisy. What is left? David? Where is David? MAF 3000. Very interesting. HMF2 is noisy because of the need to describe this, cusp very accurately in order to get that HMF2 correctly. Whereas for MAF 3000, it still reacts on the upward and downward motion because it is certainly changing, right? But it also is receptive to the density modulation as well, and they actually enhance each other. So out of that consideration, we decided to work with the MAFs. Continue on that chart, right? So this is the oblique sound in the BLUVA. Front-end transmitter, the signal goes up, reflects here, goes down there. What are the advantages of this? Doppler. When the signal goes up and down, and the wave goes vertical, not vertically, but horizontally, the Doppler is just small. Whereas on the oblique sounding, that's why all this D2D are built and operated, because the Doppler is actually the best so far indication of the TID in progress, right? So that is one of our key technologies there. And finally, there's a GNSS, my best description of that. It's also flying somewhere. The wave is flying, GNSS is flying, and we get the total density along the line. Luckily for us, it's indicative of the TID in progress, small fraction of the tech unit, but apparently because of the nice coverage in space, we can capture the TID very well with this technology, with this technique. So these are three things. Okay, let's talk about the out of 4 that I mentioned. Let's talk about LSTID quickly. So we selected a number of stations in Europe and looked at that, really visually inspecting. What did we inspect in? The terminology is we are looking for coherent velocity propagation. What does that mean? That means that all the stations that are involved indicate, yes, we see TID, it's strong, and we all see that TID goes in the same direction, reported by the sensors. When that happens, it's something that goes into catalog. All right. So, and there's like 1,600 LSTID events identified and listed and recorded above Europe. And then from that knowledge, we can approximate when TID's event started. It's approximate, but it's still good. All right. And then some averaging happening. Okay. But let's look at the MS TID. That involves even greater effort to manually analyze data. And there's the whole team that I didn't credit because there are quite a number of experts looking at the ionograms manually with their own eyes and identifying all these interesting events when happen. I'm not going to go through all the splits and spreads and satellite traces and structures and multi-cusp signatures. So there are certainly clean signatures of the MSTID. They're all cataloged and 10 stations. So it's roughly more than 100,000 ionograms were scaled specifically to identify if TID is present or not. Okay, so that was the good part. Now we are getting to the real-time data quality systems. So let's start with the HFINT. All right. So the point that I wanted to make is not on this slide for some reason. Okay. I'll probably have the later version on my laptop. Doesn't matter. I'll explain you with the hand waving approach. Okay. So if you're sitting on somewhere, right, you're looking upward and just assume that this ceiling is kind of waved, right, and it moves. I hope you sleep well tonight. doesn't come to you as a moving ceiling. Okay, so what you will see that your characteristics are changing, right? So what you can get out of it, you can get amplitude of the wave, and you can get period, and that's it. You don't know where it's going. Really, you don't. It's just you see that something is going up and down. So in order to get the direction where it's going, you need triangulation. Just like in the 50s when the TID was first discovered, you need the multiple stations. And that's why the base between the nodes is important, because otherwise, if you if the period is not, yeah, well, anyway, you can figure it out. Yeah, so it's a large scale only in that technique works today because of this physical constraint on our network, works with the large scale TIDs only, right? So triangulation. First, there are multiple triangles you can make, right? This is a beautiful example. Look, all of them are in a very much agreement about what is happening. There's a significant event, large velocities, all pointing very nicely, traveling wave southward. It's not always like that. There are some situations when, some of them detect, some of them don't. They do not agree on the direction. Possible, but we are prepared for that. So the Observatory of Abre team really spent time and came up with the at least 4 stations must agree and some other things. So that is taken care of. Missing values appears to be a difficulty. Yesterday we discussed that out of these color codes, right, with the ranging from the green to really violet or violent TID, right? So we add in a gray color to it, meaning it's just something didn't work out, right? So that we collected measurements, but we couldn't make sense of it. So that will be a gray color used for that situation. So we can do it. Missing values is another problem. That will be blank in that case. Why would we wouldn't be able to scale MAF 3000? We are doing that for decades. Instrument issues, yeah. Sporadic layer that doesn't get us to the F2 layer. D-region absorption. Low confidence of auto scaling. Remember, there are robots sitting looking at these ionograms trying to figure out what the MAF 3000 is, so there are mistakes there. Poor connectivity to the data centers. Yeah, one of the real life issues. So all that is gonna be indicated. So when the requirement is stated to us, you have to show your degradation status, okay, right? So we are prepared for that. So we will be able to report to the user that we are currently degraded. I hope it's not a secret, right? Okay. Some people say your data is not secret, but if you don't have data, that's a secret. Okay, boundary station effect. So that's it. Let me speed up a little bit. Second technique is this oblique sounding, D2D. So there are nice formulas there that allow us sitting there, watching the ceiling moving. We on oblique, think of it as like I have a laser pointer that reflects from the ceiling, goes to the floor over there when the coffee is. And if that is moving somewhere, the undulated, as the optic people say, undulated surface is moving in that direction, that signal from my laser pointer will start making circles. And we're looking at the circles and we can figure out where it goes, what the amplitude is, how big the small the circle is, and even velocity. Therefore, we can get the wavelength. So just from 2 digizons sitting on the same frequency, talking to each other. The problem, all these nice formulas that get us to the answer, they work with 6 numbers. Think about it. All we can say, all right, I see Doppler changing, I see zenith angle changing, I see azimuth angle changing. That's the period. Fourier transform. I get amplitude and phase, 6 numbers. Out of 6 numbers, I'm getting all the answers. Yeah, this is the weak point. We are so sensitive to the little data problems that may happen. The precision, you have to be careful. Bias is not important, right? We are looking at the variation, but the precision is important. We can do it, yeah, especially the amplitude. And Claudio, thank you for showing this today. Yeah, 2 or 3 beautiful charts. So best available or typical best, I don't know. Yeah. So the examples sometimes are really strong. So yeah, we can get the amplitude nicely. There are 2 southern and northern links in Europe. They say when it starts, how strong it is. So lovely. It's that direction of the travel that we figure out is kind of jittery, and sometimes it suffers from the 180-degree ambiguity, our favorite. So that's why this technique is actually, we do not suggest it for implementation. There are other difficulties. We talked a little bit today about it when the signal goes from transmitter to receiver, right? If you look at that part of it. So this is time as a horizontal axis. The vertical axis is a group path. Oh, this thing is, yeah, lovely. Okay, so you see that there are multiple ways for signal to get from the transmitter to receiver, multipath problem. On the multipath problem, this technique doesn't work. We really need a single laser pointer looking at that. We don't want 3 or 4 jammed together because multiple ways of traveling through the room. So we got an ANNA algorithm from ARTIS-5. It's an artificial neural network, pre-attentive vision algorithm that is able to sort things out into different modes of propagation. But so we see that there is a multiple ways of getting from one point to another. So we need a more elaborate tracking first, and we need a more elaborate identification second. Because this technique assumes that is a mirror reflection. That's the background of the technique, which means if that's a Pedersen ray, it doesn't work. Incorrect. So we need to rule out all and looking at this, well, these labels, of course, are there, but I put them manually because I can understand what they mean. But we need to learn how to identify these tracks and select the one that we need. And that's the one that we need. It is low elevation ray for the F2 layer. It's in progress. I promise we'll keep working on that. But that's one of the software development is ongoing, I'm saying. So we only use this technique to rule out E layer because we run our ray tricks, the ray tracing algorithm, and quickly it says which is the typical group path for the E layer signal, so we can rule out E layer. But otherwise, you see there are multiple solutions for the angle of arrival, angle of propagation of the wave. Okay, so this is just to show you that during the night there can be sporadic E layer. That came as an unusual result to me. This is nighttime. This is like 2 o'clock in the morning, and there is an ES layer with I don't know. So we picked up that ES layer as well through the single frequency propagation. It's not somebody else's. This is us. Yeah. Okay. Quality issues. HFTID method requirements are very stiff. Yes, because of these 6 values that used to derive all TID parameters, the technique uses Doppler frequencies, zenith angle, and azimuth. It does not use range or the group path, right? The group path length variation. It's a clear variation. They can see it's lovely and everything. But the technique was originally developed for listening to a powerful HF beacons. And when you're listening to a continuous signal, you don't have the sense of range. So it's unfortunate. Why? Because the azimuth variations are small. Yeah. I know, Stefan, your experience is different. This can be violent changes in your azimuth, but in our case, it's 1-2 degrees that we see jittery. So again, when the variations are small, that means we are more susceptible to the noise. So hopefully we'll, and I'm almost with my last slide for today. So there are requirements on the signal to noise ratio. The signal to noise ratio must be above 40 dB. With our typical ionogramming at 10 dB, 15 dB, with 15 dB, great. We need to get 40 dB signal to noise in order to avoid noise problems. That's why our D2D programs are running just one frequency with coherent integration time of 40 seconds, right? In order to get that signal to noise ratio right. We made one modification to the our DigiZones. Some of our DigiZone directors were victimized by Lowell sending them new cards and you know, new fans and new power supplies. But we thought if we use a longer pulse, then we will get the better signal to noise, shorten it, populate our schedules with transmissions to everywhere in Europe. That was the concept. Didn't work out yet. The problem is not in the hardware, its problem is in the software. In the hardware as well, because these longer pulses do not compress that well compared to the shorter ones. So we have a great amount of jitter, as I call it, is like a noisy spread of the signal. So we'll do that. Software will take care of it. No, software is not ready. And also that technique that we are using makes certain assumptions that are sometimes pretty far from reality. All these computations were done in assumption that the perturbation is small, not 60%, not 80%, as we see sometimes. Yeah, so it's non-linearity. Yeah, that's a tough one. Somebody help me. So that non-linear dependencies in the system, they unfortunately are there. The remaining variations are small, but yet the order of the magnitude is still okay. Yeah, compared to the carrier phase measurement error, we are still fine. Well, it won't work with your cell phone maybe, but it will work with these nice GPS receivers. Good news is that also the cycle sleep, the dreadful cycle sleep, is not an issue either. There's much progress done in this community, developing, detecting, correcting these cycle sleeps. So it should not be a problem either. So we are basically fine with the GNSS input to the data. And that was my last slide. Thank you.